For this problem, we have h of s, and it's equal to 10 over our s plus 200 over s squared plus 10s plus 6400. We were gracious enough to have this denominator be given to us in this form, which is the form if we were to factor both things separately. So we can see that this results in a complex numbers here, and to solve for this, it's going to be different than the other 14 problems that we've solved. And so the base is going to be the same though. So looking at this, we have the top part, and the top part is going to be the zeros part, and this bottom part is going to be the poles part. So when we look at the first part right here, WC of 0, well, we know that it's asking us for the omega of C at 0. And the omega here is this 200. So for the first part, our answer is just going to be 200 rads per second. Now we want to solve for the resonant frequency next, but we're going to have to do some other things first. We're going to want our equation to look something like this. It's going to be a little bit different though, since we are dealing with complex numbers. So in looking at this, we are going to first set this up by finding the omega n. And the omega n, we'll write this as step 1. It's finding the omega n. It's going to be squared, and this is equal to alpha squared plus beta squared. And then we're also going to use this Greek symbol, and then omega n, and it's equal to alpha. And with our alpha and beta, when we look in here, and this is from previous chapters, we're going to be looking at the complex part, and we only need to take one side. So we'll just look at the first part. For the complex part, we have our alpha as this value, and we have our beta as this value. So knowing that, we're going to write this in these equations, but we're going to have to rewrite these equations so they can actually look to each other. This should be equal to alpha, and now we're going to, again, rewrite them so we can plug them into each other. This should be also omega n. So rewriting our omega n, we can rewrite this as omega n is equal to the square root of our alpha squared plus our beta squared. And then we can say that our weird looking symbol is equal to the alpha over our omega n. And now we can rewrite this in each other. And this is equal to the alpha divided by the square root of our alpha squared plus our beta squared. And our values for alpha at least is 5. So we're going to have 5 there, 5 squared, plus, and then we need our beta, which is 79.844, and this is squared all underneath this squared root. This is equal to 0.625. And so that is this value. Now we're going to go into step 2. In step 2 is where we find the lower and the upper limits of our omega, and this is for the imaginary part. So we're going to write lower, and this is going to be our omega L. We're going to write upper, and this is going to be our omega, and we'll just call this U for upper. And this is going to be equal to 4.81, and then now we can plug in our values. So 4.81, and the same thing is for our upper. And then in the numerator, since it's lower, we are going to have this be raised to the negative, and then we're going to pass in this value, and then we are going to have this be multiplied by our beta. And the same thing for here, but since this is upper, it's going to have a positive, and same thing here. Now we can plug in our values, so we're going to have 4.81, we're going to have a negative 0.625, and then the same thing for here, we have 4.81, and then we have a positive 0.625, and these are both being multiplied by the beta, 79.844, and then 79.844. And so we can plug these both into the calculator, and then we're going to get that our omega L and our omega upper is equal to 72.38, and then our omega upper is equal to 88.08. And so these are our values here. Knowing this, we can solve for our omega n. For our omega n, we are going to actually take these. So I'll write a star here, because we're going to come over here. And to find this, we're going to have our omega L for lower plus our omega upper, and this is just divided by 2. And then if we do this, we are going to get approximately 80 rads per second. So we can write this in here as 80. Next, we're asked what is the value of a dB at 1 rad per second. We'll come back to this because we need our k naught for this. And to find our k naught, we're going to have to plug this part in. We're going to need our k, we're going to need the z1 and p1. And so once we have that, we can write it in this part right here, and that will solve for our a dB at 1 rad per second. So we can start writing this out though. We have a 20 log base 10, and then inside of here we're going to have our k naught. And to find our k naught, we can move on to kind of the step 3. In step 3, we want it to look something like this, and so knowing that, what we can do is we can start writing it. The first part is going to be the same, but the bottom is going to be different because it's an imaginary number. So our k is being multiplied by the z1 p1. We know that we have a 10 here, and then our z1 is 200. Our p1 is going to be the 6400. And then we're going to have this be multiplied by a 1 plus our j omega over 200. So nothing much changes with the 0. And then inside of here, we have 1 minus omega squared over 6400. And then we have plus j times a 10 omega over 6400. So what we're doing here is we're taking this bottom part, and this bottom part we're just doing the 1 minus omega squared, that's standard, and then we're going to have this over our p1, which is the 6400. We have plus j, and then the 10 omega is from the k, and then this is over our 6400. Now we found the actual bottom part. We found this earlier. So this bottom part right here is going to represent all of this. So that's going to be our omega L and our omega upper. And we can actually graph this now in the Bode diagram. So we're going to go until we hit 72.38. And this is going to look like the last factor on the page 96 of our notes linked below the like button for the phase transformation. We can see it's similar because they both have the j, and this is for imaginary numbers. And since it's in the denominator where the poles are, it's going to be going downwards. So we can start by graphing this. We know that the omega L, so the lowest part, is going to be at 72.38. Just for clarity, we can write this right here. I know it's more like 50, but since 72.38, and the next part, which is 88.08, are so close, we need to be able to see them. So we're going to go at a 0 degree angle all the way over here. So this is 0 degrees. And for this next part, it's going to be going down to 180 degrees. And so it'll be going to, let's just say about right here. This is 180 degrees. And so when we go down, we are going to want to stop at right around here. And so our line's going to look like this. And then we are going to go like this. And so we're at an angle of 180 degrees here. And this angle will be a little bit unknown, but we'll get to that in a second. And then after this, we have a k that we need to look at, our constant part. This is right here. And then if we look, this is going to be the first thing on the notes. And so this is really just a straight line at 0 degrees. So this is going to go the entire length of here. Should be straighter, but this will do. It gets the point across. We have 0 degrees here. Now we have this top part for the zeros. And this 0 is normal, nothing crazy with it. So we're going to look at the fourth factor. We know this goes from 0 over 10 to z times 10. So we can write this as 20 going to 2000, and this is at 45 degrees. So when we write this, it's going to be at 0, just like these, until it reaches 20. So that'll be about like right here. Once it hits 20, it's going to go at an angle of 45 degrees until it hits a 90 degrees, and this is going to be at 2000. 2000 we'll say is right here. Our 90 degrees, I don't know where it went, but we can just write it as right here. That way we have enough headroom. And then we can draw it out. It's going to go to right here. And so we're going to just have a straight line that goes like this. And then afterwards, it's going to go at an angle of 90 degrees. So this is 90 degrees here, 45 degrees here. And now we need to make the Bode diagram since we have all of our parts graphed out. To further check the graphing, what we can do for the polar is write the tangents like this, but in the log form. So like this. What I'm basically saying is that if we were to write this out, we would do the log form. And so this is kind of like a step 3.5. And then in the log form, we would have like 20 log base 10 of our k naught. We know that this k naught will actually solve for it. This k naught, if we were to plug this into a calculator, is 0.3125. And before we go on to here, we can actually plug this into here, 0.3125. And then we're going to get that our value is negative 10.103. So we've solved that answer. And now we can just plug in 0.3125 inside of here. Now we can keep on going and we'll do the next part. So we have a plus 20 log base 10. And then inside of here, we have 1 plus j omega over r0, which is 200. And then we have a minus 20 log base 10. And also these should be absolute value signs. And then for the next one, we have the negative 20 log base 10. And then inside of here, we are going to have the whole bottom part. So 1 minus, and then we have our omega squared over 6400. And then we are going to have a plus j times 10 over omega, 6400. And so that's going to be inside of here. This is not for our phase though. We're not going to be graphing this, but this is for the magnitude. And that's important to keep in mind. For the phase though, we'll write this as step 3.7 because it's still part of the same step. For the phase, we're going to have our omega, and then it's going to be j omega. This is actually an angle, is j omega. And then inside of here, we're going to have a tangent -1. And then inside of here, we are going to have our z, so our omega over 200. And this is going to be over 1 minus the tangent of our -1. And then we are going to have our two polars in here. We are going to have 10 omega over 6400. And this should actually only have 2 zeros. But this is then going to be divided by a 1 minus r omega squared divided by 6400. And that's how we would graph the polar. So the blue line is going to be this part right here. And then the green line would be this part right here. And we're going to actually see this when we do the Bode diagram. So we've just plotted these points right now. We haven't actually done the Bode diagram. For a Bode diagram, we need to look at all the phase inflection points. That's going to be whenever the slope changes. So that's going to be at this part. It's going to be at this part. And then it's also going to be at this part. And lastly, at this part. And so up until this 20 right here, because this is 20, everything we can see is at 0. And I'm actually going to draw this a little bit underneath, that way we can see our previous lines. So we have everything is zeroed out before 20. So that means the first part where the 5 phase inflection frequencies is going to be 20 here. Now we have to look at the differences in these slopes right here. From here to here, there's only a 45 degree angle. So this is 45 degrees. And so this is going to be the 45 degree per decade here. And this is going from our 20 to the 72.38. We see that this is where the next phase inflection is. And we can see that this slope is much steeper than this one. So we're going to be influenced a lot heavier. And what we're basically going to do is come straight down right here. We have this -180, and then it's being subtracted from our numerator. And so we are going to have it be somewhere around here. And then from here, I actually drew this a little bit off. It should be going until like around here, because it needs to line up on the column-wise part. And so it's going to look something like this. And this is going to be the straight line decrease right here. And their straight line decrease is from 72.38, and it's going to 88.08. So you have 72.38, and it's going to 88.08. Remember, there's a decimal right there, and also right there. And so now knowing this, we can keep on graphing. We have this next part. We have a up 45 degrees, and then we have a negative 180 degrees right here. So we're obviously going to be going up 45 degrees because 180 degrees is flat. So this is just going to go up at an angle of 45 degrees until it reaches right about here. So we can write this in like this, and then we have plus 45 degrees. This is also plus 45 degrees, by the way, and this is our straight line decrease. And then in our plus 45 degrees per decade, we're going to write this going from 88.08, and it's going to 2000. And then lastly, after this, we just have this 90-degree angle up here. So it's going to be going like this. And so this is going to be at 0 degrees. It'll be around the negative 190 range from this graph. Anyways, it is going to be going at 0 degrees. So from here, it's just going to be 2000. And so that is the Bode graph of all of these different parts of the graph. This is the magnitude, if we were interested in graphing that, and we could go about graphing like that. Looking at the same chart, there is a summary for the magnitude as well as the phase, but we only use the phase in this problem, and we're only concerned with the phase here. And that's how we would fill out all of these different parts.